Second part of lesson 26, friction problems involving angles. Okay, so I've demonstrated this a little in class, and we're pushing a box, and we're pushing it at an angle with an applied force of 950 newtons. So applied force right here, 950 newtons. And as we've discussed, if I'm pushing it at an angle, not all of that 950 newtons of force is being used to push the box, because the box is moving across the ground. Oops. It's moving that way. It's moving horizontally. It's moving parallel to the ground. It is not moving down here into the ground. So only a portion of the 950 newtons of force is being used to actually move the box. What portion of that 950 newtons? Well, because it's only a 20-degree angle, it's going to be quite a big portion. If I separate this vector here into components, I've got a horizontal vector and I've got a vertical vector, and you can see the x is quite a bit bigger than the y. The greater the angle, then the more force I'm wasting, because I'm trying to push it down into the ground and it's not going that way. So the best angle is 0 degrees, but depending on your height, that may be awkward to push it from that angle. So we push it at an angle 20 degrees, and you've probably figured out the first thing we're going to do here is separate the force vector into components. Oops, after we draw a free body diagram. First, draw a free body diagram. Here it is. We've got, now here's how the applied force, because we always draw from the center of the object, is actually going this way. So there's my FA. Of course, I've got gravity pulling it down, and of course, I've got the normal force pushing it up, and they are equal and opposite. Now, which way are we going to do the force of friction? Well, the force of friction is always the opposite in the direction of the motion. So it's going horizontally across the floor. This is going to be the force of friction. And there's our free body diagram. And then you ask yourself, okay, I've got vertical and horizontal components. Well, yes and no. I've definitely got two vertical and I've got one horizontal in there. But this one, the applied force, is at an angle. So that's why I must separate it into components using sine and cosine, as we did up here. So sine and cosine, let's just do that here. The sine of 20 degrees equals x over 950. Therefore, x equals, sorry, I said that wrong. It should be y. Y, we do y, the sine. And y would end up being 324.919 newtons. And to find out x, oh, I just did make the same mistake. Oh, it's tragic. Tragic. It's y. Why? Because for the x value, cosine at 20 degrees equals x over 950. We're expecting this one to be quite large, and it does. It turns out to be 892.707 newtons. So you're pushing with 950, 892 of that is being actually used to move the box. Well, apparently there's a box here, but apparently it turned into a car somewhere between the beginning and the bottom. So fair enough. Let's just go with box. Let's go with a box, because it's 49 kilograms. If you have a 49 kilogram car, it's not going to take you very far. Here we go. So we're trying to find the acceleration of the box. Why can't we just go F equals M A? We've got the force, we've got the mass. Why can't we do that? Well, we can't do that because that's the force that I'm applying, but that doesn't take into account that I've got to overcome the force of kinetic friction right here. And so all of that 892 newtons force is not necessarily being used to accelerate the object. Some of it must be used to overcome the kinetic friction. So that's where this problem becomes a lot more complicated. But now at least I've separated this into an x and a y, an x and a y, an x and a y, and that's going to help me in solving the problem. All right, so where do I need to go from here? Well, this is what I'm working towards. I'm working towards F equals ma. Now, this is the net force, and this value here is not the net force, that is the horizontal component of the applied force. So to find the net force, I'm going to have to write a net force statement for the horizontal component. So the net force statement for the horizontal component equals what? Well, it equals, let's rename this and let's call this FAX. What's that? That's the horizontal component of the applied force. FA, applied force, X means the horizontal component. So the net force equals F subscript AX plus the force of friction. Okay, that's looking good. We've got this. Oops. 92.707. All we need to find is the force of friction, which is easier said than done. So let's look at how do we calculate the force of friction. Well, the force of friction formula is this. I'm just going to write it up here for the chronography. The force of friction is this, mu Fn. Okay, and you're going, okay, that's simple. They've given us the 0.37. What's the normal force? Well, the normal force is the tricky part. So the normal force is really tricky because you have to think about this from a logical perspective. If that box is just sitting on the floor, then the normal force is easy. It's just the opposite of mg or fg. It's just mg, right? But think about this, try to apply this, think about pushing something. When I'm pushing something and I'm pushing it at an angle, I'm trying to push it into the ground. Is that having an effect on the normal force? And if you think about that intuitively, you can think, yes, I'm trying to push it into the ground. The ground is going to be pushing back with an equal and opposite force, but it's going to be more force because I'm adding all that extra force to it. When you push something at an angle, you're pushing it into the ground. Therefore, the ground must push back with an equal and opposite force. Otherwise, it will accelerate into the ground. So that's where the problem is, finding the normal force. To find the normal force, I have to look at my free body diagram, and I have to ask myself, which forces are in a vertical direction? Which forces are in a vertical direction? And here they are. You got the normal force, you got the force of gravity, and you've also got this, the y component of the applied force. So I need to use all those three forces. I'm going to write net force statement, which is going to be net force for the vertical component equals the normal force plus the force of gravity plus the applied force, the y component. So those are the three forces that are acting in a vertical direction. Now, is the box accelerating in a vertical direction? And the answer is no. So therefore, the net force is 0. Which one of these variables am I solving for? Fn. I need Fn so I can find the force of friction and plug it back in over here. So I'm solving for Fn, so I'm just going to skip a step here. We know that F net is 0. So I'm just going to say Fn equals, well, let's write it anyway, 0 minus Fg minus Fa. Right, I just took the Fg, moved it over there, took the Fa, moved it over there also, and 0 is for the F net. Okay, here we go. So now it's going to start to fall into place. Fn equals, well, we don't need the 0 there, but we need to do the negative. Fg, what's Fg? M, 49 times G. Now, do you want to use a positive or a negative here? That force is down, so we're going to go with our negative. Minus the vertical component of the applied force, which we calculated all the way back here, 324.919, positive or negative? Well, look at the free body diagram. Gravity and the vertical component of the applied force are both pointing down. So if I assign this one to be negative, I also need to assign this one to be negative. You know that's a 919. Yeah, I can't win. Anyway, having smartboard issues, obviously. Either the smartboard's not that smart or I'm not that smart. I'm definitely gonna have to go with me, unfortunately, because I can't figure out how to fix that little glitch. Anyway, we do all that and we get 805.609 newtons. That is the force, that is the normal force. All right, and that's just kind of, if the box was just sitting there, what would the normal force? It would simply be mg. So mg, you don't need to do this. I'm just doing it to solidify the ideas in this problem. That would be 480.69. So that's interesting, because if the box is just sitting there, the normal force is 480. Because you're pushing it with 900 newtons of force, the normal force is 805. So close to double the force, because you're pushing it and you're pushing it into the ground. So the ground has to push back with more force so that it doesn't accelerate. Okay, now we're looking good. Now we have the normal force, and we can go back up to this step right here, right, and find out the force of friction, and then we can go back to this step right here and find the net force. So force of friction, just go down here. Force of friction equals mu 0.49 times the normal force, 805.609, giving us a frictional force of 298.075 newtons. And now that's my friction force. I can go back up to this step here and fill that in. I'm just going to do it down here separately. So my net force, what did I have? My net force equals my applied force horizontally plus my force of friction. My applied force horizontally was 892.77. This is going to be negative 298.075 because it's in the opposite direction, giving me a net force in the x direction of 594.632 newtons. And then finally, the last step, now that we've got the net force, all that work for the net force, which we will then use to find the acceleration. Acceleration equals the net force divided by the mass. 594.632 divided by the mass, 49, giving us an acceleration of 12 meters per second per second. All that work for 12. And that's it. Yeah, that's a problem or a video you might want to watch a couple of times just to get the concepts in it, because it's a pretty important problem, and it does illuminate some of the cool points of physics and forces and dynamics and all this great stuff that we're learning. We'll see it for lesson 27, which is just as cool.